Okay, I'm back. So that is the giant impact hypothesis, and one of the reasons that we believe that that may be the story of how our moon was created is that our moon is very slowly getting away from us. Remember, Theia crashed into it, and so it would have been a huge momentum, and the pieces that shot off, some of them again would have kept on just going out into space and become other kind of asteroids. But even the parts that got caught in our orbit and accreted together to form the moon would have still had that momentum going. And so our moon is actually very slowly getting away from us. It's moving only, an inch or two a year away, but since it's been formed, that's over 238,000 miles. And so when I told you that the moonrise that looks so dramatic over the molten Earth, which of course the Earth would have been molten after it had just been slammed into by something the size of Mars, because it would have ripped the crust right off. Anyway, that newly formed moon would still have that momentum, and so is moving away from us. But even at an inch or two a year, it would have been 17 times closer back when the original event happened. Now, notice I labeled this a fun fact. When I label something a fun fact, that means it's just there because I think it's interesting. It will not be on the test or on any test. Okay, stratification of the Earth. So we have this molten Earth that, well, it was molten in the beginning, and it probably was cooling down a little bit when Theia hit it, and it was molten again. But it did eventually cool, and it's not completely cooled. The outer core and the inner core are still very, very hot, and because they're hot, that creates a living planet, but I'll get into that in the next video. Anyway, our planet is stratified, meaning that it has different layers depending on the density of the layer. And density is essentially the mass, which we weigh, as like pounds or something, divided by volume. So say you had a cube of concrete, and you had a same size cube of a marshmallow. They'd be the same size, they'd be the same volume, but the concrete cube would be much more dense because the mass, the weight of the concrete cube would be much greater than the weight or the mass of a marshmallow. And so the lighter parts of our planet, so the rocks on the surface that we see here are the light, fluffy rocks compared to, the rocks that make up the inner parts of our planet. The inner core is, I believe it's nickel and iron mostly, and mostly that's what makes up the outer core too. But the point is, the rock's material gets lighter and fluffier the closer you get to the outside. And of course, our oceans are lighter still, right? And the atmosphere is the lightest of those parts of the planet. All right, so now we're getting to the oceans. How did they get here? Well, there is a lot of different ideas. Some of the water could have come from comets, because comets are basically ice balls in space. And again, during that period early on, when the solar nebula cloud was just condensing and things were accreting, and even during the period of heavy bombardment, once the sun ignited and was blowing things around, whenever a comet crash lands on our planet, and we believe some of those comets may have been as big as 120 miles across, they're adding water to our planet. But the main reason we have water on our planet, believe it or not, is the volcanoes. Again, this has to do with density. What is coming out of the top of that volcano? Well, I'm going to show you in the next graph, but I guarantee you that it's lighter and fluffier than whatever it came from. That stuff that's up there blowing into the atmosphere used to be down in the ground. But it became too hot and volatile and light, less dense, and it got blown out onto the surface. Now, what is in the gas of a volcano? All right, this is, let's see if I put anything. No, I didn't. I'll just have to wave this around. Okay, so we got volcano. We got 3 different volcanoes here. We got tectonic styles. You don't know about those yet, so ignore that. We got temperatures. Interesting, but you can ignore that too. The only thing I want you to know is that the main 3 gases, because there's a bunch of different gases that make up volcanoes, the main 3 are water, H2O, carbon dioxide, and sulfur dioxide. Some volcanoes are as much as 97% of that stuff coming out of the top is water. Some of them, the main things coming out of the top is carbon dioxide. None of them, you know, mainly have sulfur dioxide. So really carbon dioxide and water are the main 2 things. So the water that was inside our planet, locked in rocks or not, was too light. It was not dense enough to stay down underground. And so it came out to the surface. And then it got up in the atmosphere. Once it was up in the atmosphere, it eventually condensed and formed clouds. Now at first the young planet, and there we've got our big huge moon, because you know it's just newly been formed. It's 17 times closer. And we're at the point where the planet hasn't cooled down enough to, you know, be solid rock all over. We got a lot of lava going on. We still got, look, we have asteroids, and anyway, it's a hot place, right? And water boils at 212 degrees Fahrenheit, meaning that until it got less than 212 degrees Fahrenheit, the water couldn't come down and stay down. We do have evidence that the oceans formed between, this could be on a test, 3.8 to 4.4 billion years ago. Except I won't put it like that. I'll put it in scientific notation, or I'll write the whole thing out. I want you to know that stuff that we did last week in math. I want you to understand numbers. Okay, so don't let that stuff go away. Anyway, so there's different evidence that says, and so there's a lot of argument. And the main evidence basically comes from rocks or crystals that had to have water to form. So, all right, so briefly, because briefly, life on Earth likely came from the ocean. Why do I say that? Okay, there's a lot of reasons. There's lots of evidence. One, there's fossil evidence. The fossil evidence is kind of sketchy. Some of it, you know, again, when they talk about when life evolved, okay, look down here. There we got 3.2 to 4.4 billion years ago. So we're not in agreement on that. This, for example, is supposed to be a very, very old fossil of what we've got here, cyanobacteria. These are living cyanobacteria. They say these are fossil cyanobacteria. But you can see that there could be a lot of argument about this, whether this ever used to be alive or not. But there is fossil evidence of life on this planet that's old. How old? I'm not sure. There was no ozone shield in the beginning. Life didn't show up until an ozone shield formed on our planet. Why is that important? Ozone shields protect us from, oh, I'm sorry, back up. There was no life on this planet on the ground before the ozone shield showed up. The ozone shield shields those of us that live on the ground from ultraviolet radiation. That's another reason why we believe that life formed in the ocean, because the ocean itself, the water itself, is an ozone shield. And so life could form there. It's protected from the ultraviolet radiation by the water. Also, water has unique properties that make it indispensable for life. That's why all life on this planet has water in it. Here are a couple things. It retains heat. We'll go into these later on when we talk about the chemistry of water. It's called heat capacity. It dissolves and transports nutrients, wastes, and other chemicals. It moderates temperature. Okay, these 3 properties make it so that we all need water, right? You could die of thirst way before you could die of starvation. We have to have water in our bodies, and there isn't any life on this planet, I don't believe, that is not based on water and carbon. Okay, life is mostly water, right? We're 50 to 55, 65% water. And the evidence, by the way, the life that did evolve on this planet was originally photosynthetic. So plants evolved first. And again, we have rock evidence. Now, even though this particular fossil may be subject to debate, these particular, and I'm telling you, there are microspheres from a greenstone belt in South Africa. They're 3.4 billion years old. But these particular, this fossil here is cyanobacteria formed from something called stromatolites. And there are still living stromatolites on this planet. We know that they're not in that many places. They're in Shark Bay, Australia. That's where probably this picture was taken. But this fossil here shows that we've had stromatolites, which are bacteria, on this planet for at least 3.5 billion years. Okay, let's see here. This is a famous experiment. I believe it was done in the 50s at the University of Chicago by, I believe, grad students named Miller and Urey. They had this hypothesis that on how life could have formed on this planet. So what they tried to do was they tried to replicate the Earth's early atmosphere to see if it would spontaneously form compounds that you need for life. Okay, so basically they figured out, well, we think that there would be this in the oceans and that in the oceans. We're going to put some ultraviolet radiation on this. We're going to put some electricity through this to simulate what we believe would have been electrical storms. And what happened? What happened? Okay. What they found, right? So it was basically, this was the experiment. What they found out was that at the end of a week, 10 to 15% of the carbon was now in the form of organic compounds. I believe I gave you a definition for organic back here. Yeah, it's basically a compound where the molecules contain carbon. It's a huge field of chemistry. We're not going to go into it. But for this class, organic compound means, it contains carbon. And all living things have organic compounds in them. And they found out that 2% of the carbon had formed some amino acids. Okay, amino acids are something we use to make proteins. So what they're saying is that they found out that under the conditions that existed in primitive Earth, they believed that spontaneous creation of organic compounds could be formed. Did they form life? No, they didn't form life. They formed some primitive things that are found in life. That leads to the famous question of abiogenesis. And abiogenesis basically means going from not alive to alive. How do we do that? We can't answer that question. And it's certainly way beyond the scope of this class. So for now, it's just a big word that you can learn and trot out someday to show that you went to college. You know what abiogenesis is. All right.